Hello, everyone. In this section, we're going to talk about section 9.6, absolute convergence. And we're also going to take a look at a couple of more examples of convergence tests. These are going to be the last two of the sequence of convergence tests, namely the ratio and the root tests. So that's what we're looking at here. So first, let's begin with a definition here. So what is the definition of a series that is absolutely convergence? And I have written these down for you, so I don't have to write them while talking about them. So first, the definition, suppose we have a series, sigma an. We say the series is absolutely convergent if simply the sum of the absolute value of the terms is convergent. Now, if the series is positive term series, and we've seen many of those throughout our work, then convergence is absolute. But again, it's like this: absolute value of 5 is 5. So we don't really need absolute value on it. So if a positive term, in other words, converges, it converges absolutely. But then again, it's really the same as ordinary convergence in the case of positive term series. Now, the definition of what is conditionally convergent series now. So suppose now we have a series that's sigma an. We say that this series is now conditionally convergent if it is convergent but not absolutely convergent. In other words, the absolute value of the series diverges, not convergent. So the absolute value of the series diverges. However, the series on its own will converge. So for example, to show you a quick example of this one, let's say with alternate harmonic series, right? Remember, we saw this one in the previous section, in the section on alternating series, and we established the convergence of this one in the previous section, right? We know this is convergent. This series is convergent, alternate, harmonic series. Again, we established this in the previous section that we talked, section 9.5. Now, so the series converges on its own, right? Now, let's take a look at absolute convergence for this series. That means I need to take absolute value of -1 to the n, 1 over n. And the absolute value of -1 to the n will just eliminate the sign, right? It becomes positive, and absolute value of 1 over n is simply 1 over n because the sum goes from 1 to infinity. So these terms on their own are going to be positive anyway now. And this one, remember earlier, much earlier, we established the convergence divergence of this one. And we said that this is a divergent harmonic. Okay. Therefore, the series on its own converged, but its absolute value diverged, right? Therefore, this series, so sigma -1 to the n, 1 over n, is what we call conditionally convergent. Okay, and again, all that means is that it converges on its own. And its absolute value actually doesn't. Okay, now let's take a look at our first theorem. Theorem 1 says if a series is absolutely convergent, then it is convergent. Okay, and that's kind of the definition. A series is absolutely convergent. Well, no, that was definition of what is absolute convergence. But so here's our first theorem. If a series is absolutely convergent, then it will be convergent. Okay. And well, let's take a look at our next theorem. Our next theorem is theorem on one of the two tests in this section, the ratio test. Okay, so the ratio test, and let me turn this over so you don't get sidetracked. The ratio test goes like this. Suppose we have a series. Now, this test comes in three parts, and it has to do with taking the limit of one term over another term. If the limit as n goes to infinity of a sub n plus 1, the next term, over the term prior to that, if that ratio, absolute value of that ratio, is some number, call it the limiting value. And if that number is less than 1, then the series sigma a n itself converges absolutely. So for ratio tests, again, we take the ratio of two numbers, the ratio of the next term over the term prior to that, the nth term. Now, if this ratio turns out to be greater than 1, or infinity counts, infinity is definitely bigger than 1, right? So it's greater than 1 or infinity, then it diverges. And so that means, in other words, the terms are getting too big. So that's why. So it diverges. Now, if the ratio is 1, this test is inconclusive. Means we cannot use it. So we're going to use one of the other tests, right? Convergence test. You can use direct comparison or basic comparison, limit comparison. You can use integral tests. And I have other remedial tests here that we won't talk about, but it's out there. So for example, we can use a Rabe's test, which is a generalization of a ratio test. So you can use that test, and you're welcome to, of course, research about these tests yourself. They're not in what we were doing. We have enough tests, so we don't want to add more to it. But nonetheless, you can follow it. And this is actually what that Rabe's test is. It does require that AN would be positive term in this case. And instead of looking at the ratio, absolute value of the ratio of next term to the term before, it actually uses this formula. Okay, and if the limit L exists here and L is greater than 1, then the series converges. If L is less than 1, the series diverges. And if L is equal to 1, it's inconclusive, just like the ratio test was. Now, what's interesting about this one is that L greater than 1 here is equivalent to L less than 1 in the ratio test. See that one? This one right here, L less than 1 converges. For this one, L greater than 1 converges. So there you go. This is an alternative. This happens if ratio test is inconclusive. You can use this test. Or if you want, you can use Coomer's test, which Coomer's test is generalization of the test above, Rabe's test. So it's kind of like, again, it is just generalization of that. Or you can do Bertrand's test, which is, again, the Bertrand's test is a refinement of Rabe's test. So again, any one of these would be a remedial action if the ratio test is inconclusive, or any of the other tests that we learned about. Okay. Now, let's take a look at our root test. So that was ratio test. And here is our root test. So for root test, again, you start with a series. Suppose we have some series. This time, if we take the nth root of the absolute value of an, it's not clearly, because when we say absolute value, so we're making no assumption about an to be positive term, for example. It doesn't have to be positive term series. Okay. And for this one, if the limit of the nth root of the absolute value of a n is L, less than 1 converges, greater than 1 diverges, and equal 1, just like the ratio test. This test is inconclusive, and again, we can fall on these other tests that we've talked about, or other ones that you can kind of search on the internet and through the publications or published results. And if you ever need to do this, and if none of these tests works, that means your series is fairly complicated. So you might want to ask someone in the math department to just simply help you out with this. Okay. Now, have a note here. If the absolute value diverges, but the sigma an converges on its own, this is a reminder that the series is conditionally convergent. Remember, I had that earlier. If the absolute value diverges, but the series on its own converges, and the example I cited or showed was the alternating series. Alternating series converge on their own, but their absolute value give you harmonic series, and those diverge. So alternating harmonic series, not just alternating series, sorry. So this one again, alternating harmonic series converge. Absolute value of alternating harmonic series give you simply harmonic series which diverge. So, so the sigma, the sum of an absolute or alternating harmonic series is conditionally convergent. Okay, now let's just take a look at a few examples of this. So for instance, suppose I want to show whether this series is absolutely convergent. I have -1 to the n over n root n. Okay, now the absolute value of this, I'm just going to write that, -1 to the n over n root n. When you do absolute value of it, it just becomes 1 over n root n. True? And 1 over n root n, remember that's simply 1 over n to 3/2. And 1 over n to 3/2, well, this series, we recognize this as a p-series, or we call it also a hyperharmonic series. And for this one, p is 3/2, which is greater than 1. Therefore, it converges. Okay, and because its absolute value converge, so we're going to say this is absolutely convergent. Means the absolute value of that series converged. Now, we could determine that the series converges on its own or not. This series is alternating series. So if we do alternating series, remember, if a series converges absolutely, then that would imply sigma -1 to the n over n root n converges. If the absolute value of the series converges, so does the series. So the original series converges. And we don't need to show it, but we could. The limit is 0. This is decreasing. Therefore, by alternating series tests, you can also show that. But it's redundant. We already established that. No need to do it twice. Okay, now let's take a look at, how about this one? This next example, suppose I have the sum of -1 to the, let's say, n plus 1 divided by n plus 1. We're going to look at that one. Now, this one again is alternating harmonic series, isn't it? I know it's n plus 1, but that shouldn't matter. It just changes the starting point, right? Instead of starting at 1, it starts at 1/2, but it alternates nonetheless. So this is alternating harmonic series. And because we established the convergence of that, therefore this converges. Okay, so the series converges on its own. Now let's take a look at absolute convergence. So we're looking at sigma of absolute value of an. That's the idea. So that's going to be the sigma of absolute value, -1, to the n plus 1 over n plus 1. And this is simply, we're going to lose the sign. That's the effect of absolute value. We lose -1 to the n plus 1 because now it's always positive. And there you go. Now this series is a harmonic series, right? If we start with 1 to infinity, instead of starting at 1, it starts from 1/2, a half plus a third, and so on. So this is harmonic, right? It's harmonic and it diverges. So there you go. The series on its own converged, its absolute value diverged. Therefore, this series, and therefore the original series, this one, is conditionally convergent. Okay. Let's take a look at another one. So for this next one, let's see, something that will be interesting to do. Okay, let's take a look at something that has a sine function in it. So we have -1 to the n minus 1, and let's go sine 1 over n. Okay, and we go 1 to infinity again. So for this one, again, this is alternating series, right? So the series is decreasing, and let's see, the limit n goes to infinity of sine 1 over n. As n goes to infinity, this approaches sine of 0, and sine of 0 is 0. So the limit is 0. Is it decreasing? Well, for decreasing, again, we can actually look at, let's look at f of x being sine 1 over x. Let's take the derivative, f prime of x. The derivative of sine is going to be cosine 1 over x. And chain rule times -1 over x squared, right? Now, the cosine, as x goes to infinity, let's see, cosine, or actually remember, we're looking at x greater than or equal to 1, right? For x greater than or equal to 1, so this is going to be like 1/3, 1/5, 1/7, 1/9, 1/1000. This approaches 0. Cosine of 0 approaches 1. This approaches 1 times. And of course, 1 over x squared, whether x is 5, 10, 1,000, a million, whatever, 1 over x squared is positive. Negative of that is going to be negative. So that's negative. Just call it 1 over x squared. And this is going to be less than 0. We're thinking decreasing or increasing. That's what we're doing here. The first one was the limit, right? The first one is the limit. The second one is increase or decreasing. So this means an is decreasing. In other words, a sub n plus 1 is less than or equal a sub n. All right, so we established that. Therefore, this series converges by alternating series test. So the series converges on its own. Now let's see if the absolute value of the series is going to converge. So I have absolute value of -1 to n minus 1. So I'm looking at absolute convergence now. Absolute convergence. And for this one, -1 to the n minus 1. Oh, forgot to put sign in there. That's okay. I could split it into 2 absolute values, but there you go. Let's just use my correction tape to clean the mess. Okay, so here's that, and then the sign of 1 over n there. And when we do this one, what are we going to get? We're just going to get simply sine sigma of sine 1 over n. Now, as n goes to as n from 1 to infinity. Now, how do we work this one? Let's see. Does this series converge or diverge? Because this is like sine 1 plus sine 1/2 plus sine 1/3 plus sine 1/4. So the signs are going to fluctuate between 1 and -1, right? The value. So for this one, I'm going to use, let's see, because this is 1 over n, let's do this. I'm going to let a second series be n. Let this series be 1 over n. Okay. And then I'm going to look at, so 1 over n, this is a divergent harmonic, right? That's the series that I picked. Harmonic. Okay. Now, sorry, there you go. Harmonic. Now, let's do a limit comparison test. We're going to do the limit of an to bn as n goes to infinity. And that's going to be the limit in going to infinity of an. Remember, an is the original series, sine 1 over n, divided by 1 over n. Now this one, this limit is one of the limits that we worked in first semester calculus. You can let x be 1 over n. Now, as n goes to infinity, 1 over n goes to 0. X approaches 0. So the limit is going to be the same as x going to 0 of sine 1 over n is x, so that's sine x over x. And this limit, again, in Calc 1, we showed this is 1. If you want, you can actually use Hospital on this because sine of 0 is 0 over 0, indeterminate form. You can also use Hospital if you want. Take the derivative of the top, derivative of the bottom, and the answer should be 1. Nonetheless, what we wanted to know is convergence or divergence of this series. Therefore, this thing, because the harmonic diverges, the ratio of them is 1, right? And that limit 1 is greater than 0. So by LCT, the limit comparison tests, they both have to diverge because 1 over n diverges. By LCT, sigma of sine 1 over n diverges. Okay. Now, let's see. The series on its own converged, right? That series converged on its own. This one converged by itself. But then we just showed that the absolute value of the series, right? The absolute value of the series diverged. So this series is therefore conditionally convergent, right? So this one, we're just going to write conditionally convergent. That's what this one is. Okay. So again, there's a lot of these that we can look at. Let's see. Let's take a look at something a little more involved, a little more challenging. So I'm going to look at this series in my example. We're going to look at the sum of n factorial squared divided by 3n factorial. Okay, we're going to look at that series. Now, this is the series of positive terms. Okay, it just happens to be positive. Now, because it involves factorials, let's actually do a ratio test on this one. Okay, so I'm going to write RAT. That's short for ratio test. So for ratio test, remember, we have limit of the absolute value of an plus 1 over an, and n goes to infinity. And of course, the terms are positive, so absolute value doesn't matter in this case. So I'm just going to go the limit n goes to infinity of the next term divided by the term prior. So I'm going to change n to n plus 1. So it's going to be n plus 1 factorial, and then the quantity squared. That's the numerator of the fraction. Over the denominator is n plus 1. So it's going to be 3 times n plus 1 factorial. Now, to divide by an means to divide by the fraction. Well, I don't want to divide by fraction, so I'm going to flip or invert and multiply. So that's going to be n factorial. Actually, invert, so it's 3n factorial, right, over n factorial squared. All right, now let's take the limit. The limit as n goes to infinity of this one. Well, we can actually work this one out. N plus 1 factorial, isn't that n plus 1 times n factorial? You square it, divided by, I'm going to write this n factorial directly below it, because you see the similarity here. The numerator is n factorial squared, n plus 1 squared. So the n factorial squared and n factorial squared, that these two cancel. And then let's see, in the numerator, what do I have? I have 3n factorial. We're going to keep that one. 3n factorial. Now, that's in parentheses, just so I'm not tempted to multiply 3 times n factorial. It's 3n quantity factorial. All right. So this is just going to remain as 3n parentheses factorial. Now, in the denominator, I have 3n plus 1. 3n plus 1 means 3n plus 3 once you distribute, write this, and then factorial it. Well, what does that factorial look like? This one. This looks like 3n plus 3, and then 1 less than that. 3n plus 2, 1 less than that. 3n plus 1, 1 less than that is 3n. And we're going to stop factorial it. Okay, and then I can cross out 3n factorials. And remember, the n factorial squared and n factorial squared is gone. So this is simply the limit. N goes to infinity of, in the denominator, we have 3n plus 3. And what else do we have? We have 3n plus 2. And we have 3n plus 1. And that's it. In the numerator, we have n plus 1 squared. Okay. Notice in the numerator, we have a second degree polynomial. In the denominator, we have 3n, 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 which is the first term of the product is 27n cubed. So you have n squared over n cubed. Divide the top bottom by n cubed, and you will see that this limit approaches 0 because the degree of the polynomial on top is less than the degree of the polynomial on the bottom. And 0 is less than 1, converges. And it converges absolutely, right? So we went for absolute convergence. And so by ratio tests, that's a series converges. So that's a good thing, I suppose. And let's see. let's take a look at, I haven't done any root test, right? So let me maybe do an example of a root test for you, and then that should be enough. What we want to do. Let's see. Root. Okay, for the root test. Trying to see if I can find a decent example for you folks. Let's take a look. Most of the ones I actually have done are by ratio test. So let me hold on here. Okay, so let's take a look at this one. This is example of a root test. Okay, so let's take a look at this one. So for this one, I'm going to look at the series is -1 to the n over, and let's go n plus 1 times the arc tan of n quantity to the nth power. Okay. Now, for this one, how do I know, by the way, that I need to use the root test? Because I have something to the nth power. When you take the nth root of the nth power, then you get rid of the power, right? So let's do a root test. So I'm going to look at the limit as n goes to infinity of the nth root of the absolute value of an. Now remember what absolute value does here. The absolute value gets rid of the -1 to the n part. So I'm just going to drop that part out. Okay, this is going to be the limit as n goes to infinity of. Drop the -1 to the n, and it's going to be the nth root of this expression, n plus 1 arctan n to the nth power. And you can see now the n's cross out here, right? The nth root and the nth power cross out. And now we can rewrite, let's see, what does the root look like? So this is going to be, we're simply going to lose the root. It's going to be the limit n to infinity of n plus 1 times the arctan of n. Now, as n goes to infinity, remember the arctan approaches what? Pi over 2, right? We know that one. This approaches pi over 2. N plus 1, that goes to infinity, right? So let's see. Yeah, so for this one, this approaches infinity. This limit approaches infinity, which for this one again, it's going to, so how is this going to work? It's going to diverge, right? And let's check this one. All right. Again, if it's positive or infinity, this is greater than 1. Therefore, sigma an diverges. Okay. So by root test, this thing diverges. Now, the absolute value, by the way, here, absolute value of this diversion, the series on its own, if you do this, it will be more complicated to do this one, right? If you want to do AST on this one, it will be more complicated. Now let's change this one ever slightly, okay? This one, I'm gonna now write it as a sigma of, let's go the nth root of n minus 1 to the power of n. Okay. And we're going to take the root test with this one. We're going to choose the root test. So this is going to be the limit of the nth root of the absolute values, which is going to be the nth root of nth root of n minus 1 to the nth power. Okay, now the n's cancel here, right? So what we're going to end up is simply the limit of the nth root of n minus 1 as n goes to infinity. Okay, now the nth root of n as n goes to infinity, this one, we can write it as n to 1 over n as a rational exponent. And this limit as n goes to infinity, well, that's going to be infinity to 0. And infinity to 0 is indeterminate form. Okay, so that is an indeterminate form. So that means we need to work this one. How do we work this one? Let's actually take the derivative. Okay, let's take the derivative of this. And we're going to actually, well, before we take derivative, let's take the limit of the natural log of this. The limit of the natural log of it. So if y is n to 1 over n, we want to do the limit of the natural log of y. That's what we want to do. Okay, so let's see. The natural log of y here is going to be that part. Natural log of y is going to be 1 over n ln of n. And now we're going to take the limit as n goes to infinity of the natural log of y. So that would be the limit n going to infinity of 1 over n times natural log of n. And at this point, the indeterminate form is 1 over infinity approaches 0. And the natural log of n and infinity approaches infinity. So now we have the indeterminate form 0 times infinity. We can rewrite this one as the limit of the natural log of n over n as n goes to infinity. And now we have the indeterminate form infinity over infinity. And now we can do Hospital on this one, right? If we apply Hospital, we're going to get the limit n approaching infinity of 1 over n over 1, which is 1 over n, right? The limit of 1 over n. And that limit, 1 over infinity, approaches 0. So the limit of the natural log of y is 0, therefore. And remember, we can say that's natural log of the limit of y as n goes to infinity. That turned out to be 0. And the natural log is log base e of the limit of y. Y is the original function here. Y is the original. And we can go by definition of logarithms, rewrite it in exponential form. That's going to be the limit of y as n approaches infinity, which is e to 0 or simply 1. And there you have it. So this limit turns out to be 1. What did we just find out? Let's go back here and complete it. So the limit of nth root of n is 1. So that's going to be 1 minus the limit of 1 is 1. Doesn't matter n because it doesn't depend on n. And that limit is 0. Okay. And because 0 is less than 1, so this the series, in this case, we say converges. The original series converges by the root test. And there you have the result of this one. Okay. So there you have it. So we're done with this section. Hopefully, again, everybody's okay. And we did some really good examples for both the root and ratio test. This one was the root test we did. The one above that was also a root test that we did. All right. Thank you for your attention, everyone, and have a good day.